What is a binomial and what is the binomial theorem? Bi means two, and in classical mathematics, nomial is another word for term. In the generic example a plus b to the power n, each of the term inside is called a monomial, which means one term in it. A is the first monomial and b is the second monomial. When we say binomial expansion, we mean the expansion of two monomials, hence a binomial raised to a power. In this example here, there are two monomials a and b together called a binomial, and when raised to a power of some value, say n equals 5, results in an expansion with many terms in it, hence called binomial expansion. To discover the binomial theorem, let's expand the binomial a plus b to a series of powers from 0 till 6. The first one, that is a plus b to the power 0, equals 1, and that's based on one of the laws of indices that says anything raised to the power of 0 is 1, so this would be 1. Next, a plus b to the power of 1 will repeat the terms in the bracket, and that's it. Next, a plus b to the power 2, that is a plus b squared, which is a plus b multiplied by a plus b. You can use the rainbow expansion method and multiply out each of the term, or you can simply recall the expansion formula from memory. That is square of the first monomial plus 2 times the first and the second monomial plus square of the second. Now how about the power of 3? You can work it out using the rainbow method, or we can use the previous expansion and apply the rainbow method, and that would eventually result in these terms arranged in decreasing powers of the first monomial, that is a. The rest of the powers likewise, but surely it's with increasing difficulty, as you can see here. Note that in each of these expansions we have chosen to arrange the terms in decreasing powers of the first monomial, that is a, and that results in some interesting observation. Firstly, the coefficients of the first and the last terms are 1, and the coefficients are symmetrical. Consider the binomial raised to the power of 6. The coefficients are 1, 1, 6, 6, 15, 15, about the middle, which is 20. Secondly, the powers applied on a, which is the first monomial, in each expansion decreases by 1 for each consecutive term in the expansion. 2, 1, 0, 3, 2, 1, 0, 4, 3, 2, 1, 0, 5, 4, 3, 2, 1, 0, 6, 5, 4, 3, 2, 1, 0. On the other hand, the powers applied on b, which is the second monomial, are in the increasing. 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, 5, 6. And the sum of the powers contributed by each of the monomial in each of the term equals n. That is the power to which the binomial was raised. Consider the binomial raised to the power of 5. The sum of the powers contributed by each of the monomials in each of the terms equals 5. 0 plus 5, 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1, and 5 plus 0, they equal 5. Thirdly, the number of terms in each expansion is 1 more than the power to which it was raised. To the power of 0, 1 term in expansion. To the power of 1, 2 terms in expansion. To the power of 2, 3 terms. To the power of 3, 4 terms. To the power of 4, 5 terms. To the power of 5, 6 terms. And to the power of 6, there are 7 terms in expansion. The number of terms in the expansion is therefore n plus 1. There is definitely a pattern emerging from the observation we have made, and knowing the pattern here will help us derive the terms without the tedious rainbow multiplication method and to get a specific term from the expansion without actually expanding the binomial. Let's look at the binomial raised to the power 4 more closely, which basically is a plus b multiplied with itself 4 times. That is 4 factors, and when you expand them, you get these terms. The coefficients of the first and the last term should be 1. The powers of the first monomial, that is a, should be in decreasing order, 4, 3, 2, 1, 0, while that of the second monomial, that is b, should be in increasing order, 0, 1, 2, 3, 4. And the sum of the powers contributed by each monomial in each of the terms should be 4, and there should be a total of 5 terms in the expansion. You must take note that the coefficients of the two monomials here are 1. Mathematicians eventually discovered and realized that the coefficients of this simple binomial expansions with coefficients of 1 follows the laws of combinatorics. Now, what is that? Looking at our example here, the only way we could get an a to the power 4 term from this expansion is if we have a from each of the factors multiplied and only one such term is possible, therefore we put a 1. The second term is a cubed b, and let's trace the ways we could get that term out of this expansion. We could get AAAB, AABA, ABAA, BAAA. In total, we have 4 multiplication paths, and that results in an a cubed b, hence the origin of the 4. The third term is a square b square, and let's trace the ways we could get that term. We could get AABB, ABAB, BAAB, BABA, BBAA, and finally ABBA. In total, we have 6 multiplication paths that results in the term a square b square, hence the origin of the 6. And similarly for the last 2 terms in the expansion. From the study of combinatorics, the coefficients here, which represents the possible ways of obtaining these combinations, can be simply obtained by using the equation NCR. The study of the derivation and validity of this equation is not in the scope of our lesson here. However, with the right value of n and of r, the equation can be used to obtain the series of coefficients called the binomial coefficients. The value of n, which is the power raised, is the same while the value of r starts from 0 and increments by 1 for each subsequent term. They are pronounced 4c0, 4c1, 4c2, 4c3 and 4c4, and when entered into the calculator or evaluated using the given equation, will give the binomial coefficients. From what we have discovered so far in this lesson, to obtain the terms in the expansion, we have to consider the contributions of the binomial coefficient, the first monomial and its power, and the second monomial and its power, for which a trend or pattern had been just observed. And we shall see the derivation of the general formula for the terms in the binomial expansion in the next lesson.